Hi everybody, I hope you liked the video on Trabomi, although I assume that most of you already knew. So that's why we have an additional video this week with a topic which provides us new insights in radiative transfer in a new spectral range, the so-called thermal infrared spectral range. I think it was 2 weeks ago that we discussed the two energy states of an atom or molecule, where we assumed that the population of these two states can be described by the Boltzmann distribution for a certain temperature T, which means that these two energy states are what we call in local thermal equilibrium. Under this assumption, the radiation field, which is in equilibrium with the matter, is given by the Planck function. But we do see here in the frequency representation, so B nu as a function of temperature is equal to 2 times the Planck quantum h frequency to the power of 3, and in the denominator we see here the speed of light, and then we have here the exponential coming from the Boltzmann distribution e to the power of h nu divided by the Boltzmann constant kb and temperature, and all that minus 1. It is actually remarkable that this Planck function includes 3 constants of nature: the speed of light, the Boltzmann constant, and the Planck quantum. And I think there, not that I know, other laws which combine so many constants, natural constants. Anyhow, this is only a side remark. What we can do now is we can determine the maximum where the radiance, which is described by the Planck function, it has its maximum. So what we do is we derive the derivative of B nu with respect to the frequency. We require that that is 0, and doing so we can reformulate that equation in the form 3 times the exponential function to the power of minus x, x we will define in a second, minus 1 equal to x. So that is equivalent to setting the derivative to 0, where x is the ratio of Planck constant h times frequency divided by Boltzmann constant times temperature. And this equation you can solve, and you find that x is equal to 2.821, whatever this number actually means, and that gives us that the frequency for which our Planck function has its maximum is this constant 2.821 times times Boltzmann constant temperature divided by Planck constant. It means that the maximum changes with temperature. The higher the temperature, the higher the frequency where that maximum occurs. And this is called the Wien's displacement law. I think last time we already talked about the fact that the Planck function can be given in at least two different notations. We can also express the Planck function in terms of wavelength instead of frequency. And therefore, to do this transformation, we have to account for the fact that the Planck function is a distribution function. It describes the energy distribution of the radiation field. Therefore, we have to do the transformation as follows. We consider a frequency bin, d nu, times the amount of radiation which is in that bin, B nu at temperature T. And that is now written as the Planck function, where we simply substitute nu as a function of lambda. So this becomes an expression of lambda, of the wavelength. And then we have to take into account, in addition, the Jacobian of the transformation, the derivative d nu with respect to lambda, then d lambda. So that is the proper way how to transform distribution functions. And doing so, we see that this is then our Planck function as a function of wavelength, which is shown here. We indicate that by the subscript lambda to the b, right? And when we do so, when we calculate this derivative, which is c divided by minus lambda to the square, the absolute value, then we have here the recipe to calculate that function. And what it then gives is that the Planck function as a function of wavelength is 2 times hc square lambda to the minus 5, and then in the exponent the expression that we already know, but in addition a lambda here in the exponent. So hc divided by Boltzmann constant times t times wavelength, and all that minus 1. So we can also for that function determine the maximum, and the recipe is exactly the same. We calculate the derivative with respect to lambda, and that yields us the following equation, which really looks different from the one that we already had. X minus 5 e to the power of x is equal to minus 5. The variable x is the same as before. You can solve that equation and you get that x is about 5. So the Wien's displacement law for the Planck function as a function of wavelength looks different. It says that the maximum wavelength is hc divided by 5 times Boltzmann constant and t. That again can be transformed into what frequency, so which frequency belongs to that wavelength, and then we get back our original expression that the frequency is proportional to temperature, but now with a factor of 5. And that's really weird. So to answer the question, where's the maximum of the Planck function, means that you can get two answers. One if you give it in the frequency representation, and another if you give this function in the wavelength representation. That needs a little bit more discussion, how we should interpret that. Before we proceed with our discussion, let us have a look how the Planck function look like. And what we do see here in this graph is the irradiance as a function of wavelength on 2 logarithmic scales, and we have here 2 solid lines, and that is the Planck radiation at for a body at 6000 Kelvin and at 300 Kelvin. 6000, that is the equivalent temperature for the radiation of the sun. 300 Kelvin, a typical value for the Earth's surface. And what we see is that this function, which is by the way here given in the wavelength representation, that's not because we see the wavelength on the x-axis, but we see that in the units. It's per micrometer, so a wavelength unit. So in that representation, we see that let us call the solar Planck function for a temperature of 6000 Kelvin has its maximum at, say, 550 nanometer. Whereas the Planck function for the Earth, with a temperature of 300 Kelvin, has its maximum at 10 micrometer. And you can be sure that changing the representation, the whole shape of the Planck function will change, and by that also its maximum. So that is something we want to discuss, but before doing so, a few other remarks, which are also, I think, quite important when we see this graph. The first thing is that the Planck radiation of the sun is always on top of that of the Earth, of the entire spectral range, for sure in the UV, but even where we have our maximum in the thermal emission of the Earth, the sun is, 2 to 3 orders of magnitude larger than the signal coming from the Earth. So you may conclude from that figure that actually the whole emission of the Earth is completely irrelevant, particularly when we want to investigate the energy budget climate related aspects. But that's not true, because we did actually two mistakes. Two mistakes that I would like to discuss a little bit in more depth. The first one is that we didn't account correctly for the distance on Earth. We do know, and that was discussed, I think, in lecture 3-4, that the irradiance for point sources changes with the distance from the origin of that point source, and it changes with 1 over r square. It's the contribution of Copernicus that we discussed at that lecture. So having this knowledge, and let us now assume that we have a flux or irradiance F0 at the sun surface at a distance r sun, that is the radius of the sun. And now we can calculate the corresponding irradiance at the top of atmosphere of the Earth using the law that it changes with 1 over r squared. It means that the solar irradiance changes with r to the power of 2 sun, that is the sun radius, divided by the distance between sun and Earth, also in square, times the flux at the surface of the sun. Now, the Planck function is actually an irradiance which we have to translate to an irradiance, and therefore we have to apply a factor of pi to the Planck curve. That is simply assuming that the radiation is isotropic, the thermal infrared radiation, which is the case. We know that. Then the integration over all directions over one sphere, half sphere, gives us the factor of pi. And I believe this is actually accounted for in this graph to get this figure. But what is not accounted for is the scaling of the different distances. Doing so, we get, instead of the upper solid curve for 6000 Kelvin, the dashed curve. So it's already significantly reduced. But this is only one aspect. There's another point quite important, particularly when we want to talk about climate relevant aspects. And that is, simply said, because the sun is a pencil beam, but thermal infrared radiation is emitted isotropically in all directions, right? So when we are at the top of the atmosphere, we only get contributions in a very narrow angle range. But at the bottom, the Earth's surface emits radiation isotropically in all directions upward. So what is actually, when we calculate from that situation fluxes, what is actually then the factor that we have to apply to compare solar fluxes with those of the Earth thermal infrared radiation? First of all, we make use of the fact that the sun has an opening angle of 0.5 degrees, so a very narrow spot on the sky. This information we can use to calculate the solid angle, because we want to compare actual angles here, and that is pretty simple. Just consider that as the spot of the sun. That is the solid angle. We have here half of the opening angle, alpha, 0.25 degree. We can calculate the radius of the disk simply by geometry. That's the tangent of the half of the opening angle of alpha times the distance between the Earth or the observer and the sun. And doing so, we can then directly go in the next step, where we calculate the solid angle for that geometry, pi r squared divided by the square of the distance, and that is pi times the tangent square alpha, which is 6 times 10 to the minus 5 steradians. Alright, so we do know now the solid angle of the solar beam, and now we have to compare that with the integrated signal of the Earth emitted thermal infrared radiances over the upper hemisphere. So we have to take into account, in addition, 2 pi, and that already shows us that we have to deal here with a factor of 10 to the minus 5 difference between the solar flux and the flux in the thermal infrared. So let us come back to the question we already asked about the meaning of this maximum of the Planck function, or if it really has a physical meaning, let's say it like that. The key problem that we have is, and I just want to repeat that here, that the two functions, the frequency and the wavelength representation of the Planck radiation, are two different distribution functions. The one gives the distribution in terms of a frequency bin, and the other one in terms of a wavelength bin. And if you want to compare these two distributions, you shouldn't do that by value, but always considering integrals of that function over corresponding intervals. So you can compare an integration of the frequency representation of the Planck function over a window from nu1 to nu2, and then you have to integrate the wavelength representation over a corresponding wavelength interval, which I call here lambda 2 to lambda 1, where the frequency and the wavelength are related by this dispersion relation that we already derived relatively early in that lecture, right? And doing so, we really compare the same things. So that is the way how we can deal with these two different representations, but not looking at individual values. And that makes the displacement law of Wien a bit difficult to use, particularly if we want to give the maximum a certain interpretation. Before discussing that in more detail with a very nice example, I want to just say a few words about two approximations of the Planck radiation. The first one is the Rayleigh-Jeans approximation, which is the radiation law when we assume large wavelength, extremely large wavelength, or extremely low frequency. And then in this particular case, you can show that the Planck curve can be approximated by a relation which is linear in temperature. 2 times the Boltzmann constant times the temperature times the frequency squared divided by the speed of light squared. Similar, in the wavelength representation, it is 2 times Boltzmann constant t speed of light divided by lambda to the power of 4. That is a very interesting approximation, and it has the effect that when you observe objects of very high temperature in the visible, for example, you can apply this approximation because you are in the tail of our Planck curve. And so you can find a one-to-one correspondence of a radiometric quantity and temperature. And particularly in astronomy, where people look at hot stars, they specify radiation in temperature using this relation. I also want to mention here the Wien approximation, which is just the opposite. Wavelength should be short, frequency should be large, and what we see then is that the two Planck functions are simplified in the sense that we have here now 2 frequency to the power 3 divided by the speed of light to the in square here our exponential, and in the wavelength notation very similar to Planck quantum c squared divided by lambda to the 5 and the exponential function. Alright. So after this little discussion on the different approximations, we come back to our main topic, the Planck function, and what can go wrong when we interpret it value by value. And therefore, we start our discussion with the so-called luminance efficiency of the human eye. It's a function which describes the brightness sensitivity of the human eye, here as given as a function of wavelength. And the so-called luminance L is given by that spectral integral, where we integrate the solar spectrum, here the radiance I of lambda, and we weight them by the luminance efficiency. And here we have an integral over wavelength and the constant k to convert units. And the interesting aspect is when you want to change that integral, instead of over wavelength, you want to calculate it over frequency. The function really doesn't change really. The only thing that you have to do here is to change the variable. Instead of nu, you c divided by lambda using the dispersion relation, which doesn't really affect the shape of that function, only this 1 over lambda that you have. But the maximum stays at the maximum, that's for sure. This is definitely not true for radiances, because radiances, as is same as for the Planck curve, it's a distribution function of energy. So when you want to convert that, there you have to apply the Jacobian of the transformation function as we discussed. Okay. Now a few words about this fluorescence, and not fluorescence, about this luminance, and therefore we want to discuss a fluorescent shade which absorbs light in the UV and re-emits it in the visible. And what it actually does, it transforms energy from part where our eye is little sensitive to brightness to a spectral range where it's extremely sensitive to the maximum. And then you get these effects that you see here, that these effects of fluorescence, they look extremely bright to our human eyes. How does this luminance efficiency look like? That is the curve which is related to the function v that we have introduced. It has its maximum at 550 nanometer. So what happened in the previous slide, you shift energy from the UV into the visible, and there you see then the same energy with a much higher brightness. At least you think you see it because of your sensitivity of your eye. So, now the point that I want to raise. Some biologists stated that the current luminance efficiency has its maximum at 550 nanometer, which corresponds to the maximum of the Planck curve in frequency because of evolution. So the evolution process caused a selection such that this function peaks at the peak of the Planck curve, and because of that our way how we see things is optimized. But that's a bit now a weird argument, because we know that the maximum in frequency is not the same as the maximum in wavelength, which peaks at a different wavelength. So how should we understand now this statement? Because evolution doesn't know about math and integrals and transformations of variables, for sure not. It doesn't prefer here one way or the other. So actually, I think the only way how we can what we can conclude from this observation is that it's just coincidence that the maximum of the frequency representation of the Planck function of 6,000 Kelvin is at the maximum of the luminance efficiency. So really just by accident, which doesn't mean that there may be another process which triggers evolution for that to favor that luminance efficiency, but the way as it is described, that it is linked to the maximum of the Planck curve, is not correct. And to illustrate that in a simple slide, again, here we have the wavelength representation with its maximum at 500 nanometer. We have here the maximum of the luminance curve close to it, and when we change variables here as a function of frequency, the maximum now is suddenly at 900 micrometer, 900 nanometer, which is far away from actually the maximum of the luminance efficiency curve. So that can't be the reason to choose to let evolution choose for that luminance curve. I think this discussion nicely illustrated how careful we must be when we look at the Planck function and its values, and that the only way or the proper way to interpret the Planck curve is looking at integrals. That brings us to another law, the so-called Stefan Boltzmann law, which describes the entire energy which is described by the Planck function. So we have to integrate the Planck function over the entire range of frequency or wavelength, and it doesn't matter what you do, wavelength or frequency. Here we use the frequency representation. So the integral goes from 0 to infinity. And the first thing what we do is to solve that integral, we introduce our new variable x, the ratio of photon energy divided by Boltzmann constant B times t. And having done so, we in addition account for the Jacobian of the transformation d nu dx, which we can calculate straightforward. And after all that, this integral can be expressed as a factor which has here the temperature to the power of 4 in the numerator, and the rest, those are constants. And then the integral from 0 to infinity dx, x to the power of 3 divided by ex minus 1. Now, that integral can be solved. You get a certain value for that. And finally, what this law then says, that the total integrated energy is the so-called Stefan Boltzmann constant sigma divided by pi times the temperature to the power of 4. In other words, the Stefan Boltzmann law states that the total energy radiated per unit area of a black body across all wavelengths per unit time, that is the interpretation of that integral, is directly proportional to the fourth power of the thermodynamic temperature T of that body. And next week we will use that law to discuss the greenhouse effect in a little bit more depth. So that's why I would like to introduce it here. So we discussed Planck radiation, which is also called black body radiation, and we must realize that a black body is a really ideal case. There's no real black body in nature. So it's absolutely required to say a few words about gray bodies, because that's reality. Still, we start this discussion assuming now a black body inside a cavity of Planck radiation. So that is our situation. We have our cavity, our container, the walls we put on a constant temperature, and after some time we get a thermal equilibrium, and inside our container we have the Planck radiation of the temperature T. And now we put another body inside our cavity of the same temperature. So we actually put it in a bath of black body radiation. And what we do is now we calculate the absorbed energy per area of our body in our container. And doing so, we end up with the integral that we have to calculate from frequency 0 to infinity of the Planck radiation. Actually, that's exactly the integral that we just discussed. But here we want to do now something else. We ask now how much radiation is also emitted by that body. Because if it only absorbs light, then the temperature will increase, and that is definitely not a thermal equilibrium. So it must emit radiation, and the amount of radiation that it emits can be calculated as the integral from 0 to infinity over frequency of the spectral emitted radiation. And obviously, when our situation is in equilibrium, both must be the same, otherwise we would get a change in temperature of our body. Now we do one step further. We use an argument of symmetry. We say that actually all physical processes should actually follow the time reversal symmetry, which means that when we change the direction of the time direction of a process, the process still should be the same. And absorption and emission is just a change in our time axis. And because of that argument, we say that this statement is not only true for the integrated quantities, but it's actually true for each individual frequency or each individual photon, each individual process. And now we replace our body by a gray body. So what does it mean that it is gray? Actually, it only absorbs a certain fraction of the light which illuminates the body, and it also emits only a certain fraction of that light. And now we can use the same argument as before and just say that the total amount of absorbed radiation, here the integral over frequency, and now we have the absorptivity, which is the fraction of the absorbed radiation times the Planck radiation. So that integral gives us the total amount of absorbed radiation. And that must be equal to the one of the emitted radiation, otherwise we are not in equilibrium, which is the corresponding frequency integral over the emissivity, so the fraction of the emitted light times the Planck radiation. Again, using arguments of thermal equilibrium, this only holds for the integral. So there may frequencies where it's not valid but compensated by other frequency. However, now we apply the same argument of time reversal symmetry as above, and that means that the absorptivity must be equal to the emissivity whenever we are in the thermal equilibrium. And that is the law of Kirchhoff. We can formulate the Kirchhoff's law even in a more general way, and you have seen already how what we did. The equation was actually from thermodynamics only true in the integrated form where we consider the entire energy in the spectrum, but because of the time reversal symmetry we said it's even true for each frequency. We can now go even a step further and can say that there's also a directional component that we haven't considered yet. And therefore we define the emissivity epsilon as a function of frequency, direction omega, and temperature T as the ratio of the emitted radiance at frequency nu and direction omega with respect to the corresponding Planck radiation of temperature T. And we define the absorptivity as the absorbed radiance with respect to the incoming radiance, both functions of frequency and direction. And here even polarization can be considered, but let's make things not too complicated. When we are in thermal equilibrium, the incident radiation of the absorptivity is the Planck radiation, and then Kirchhoff's law holds for the emissivity as a function not only of frequency nu, but also of direction and temperature, and that this is equal to the corresponding absorptivity. So we talk about absorbed light, but what actually happens with the fraction of light which is not absorbed? Because of energy conservation, it must be reflected. There's no other way around that. So we have to find a way how to formulate now the amount of radiation which is reflected. And now I do one step back. Instead of using the complex notation of the emissivity and absorptivity, I just assume that we have an emissivity and absorptivity which is independent of direction, as we discussed before. And in this case, we can express the absorptivity as it is defined here, so ratio of radiances. It is equal to a ratio of fluxes. So the absorptivity is the absorbed flux divided by the incoming or the incident flux. And this expression remains as to the definition of an albedo, where instead of the absorbed flux we had here the reflected flux. And because of that we can say the albedo, the spectral albedo, as a function of a body, as a function of frequency and of a function of t, is 1 minus the absorptivity, and that is then the ratio of the corresponding fluxes, the reflected flux divided by the incoming flux. With that, now we have all tools at hand to discuss radiative transfer in the thermal infrared. We already discussed the radiative transfer equation. Remember 2 weeks ago, lecture 8, where we studied the two-level system to describe an atom or a molecule and a radiation transition process. And then we assumed that the population of these energy levels was given by a Boltzmann distribution, and doing so we could show that the radiation field, which is in thermal equilibrium to the matter, can be described by the Planck function. And we went one step further and we derived the radiative transfer equation, which says what is the change of the radiance along a certain distance ds. And then we came up with that equation, where we see that the first term is the Bouguer-Lambert-Beer's absorption law. We have the cross-section, sigma, at a certain frequency times the total number of particles in a certain volume, that is the density, times then the radiance, and then we have in addition the source function. And that is the black body radiation source function given by the Planck curve, Planck function. This function already tells us the Kirchhoff's law. It says something about absorption and emission. The first term on the right hand side, that is the amount of absorption, and the absorptivity is nothing else than sigma times the density. The emission is described by the Planck function, and the corresponding term in front of it, that's the emissivity. It's again sigma times the density. So absorptivity and emissivity is equal, and that is Kirchhoff's law. Obviously we want to solve that differential equation. We want to solve that to get the radiance at a certain position in a certain direction, and we want to do that to understand measurements. And here we see one measurement for the geometry of a satellite in orbit looking down to the Earth. It's a Fourier transform spectrometer on the Nimbus 4 satellite, and the curve with these wiggles, that is the measurement as a function of wavelength or wave number, and on the y-axis the radiances, here given in the frequency notation, right? So what we see is that we have here certain absorption features. For example, here at 15 micrometer we have a CO2 absorption,
That is noise absorption here at 9.6 micrometer, and I think that is water vapor if I remember right. So whenever there's a telluric absorption, we see here also a feature in the emitted radiances. But when we do not have a telluric absorption present in the spectrum, then we see a kind of continuum function here and there. And that is actually the radiation which comes from the Earth's surface here at, I don't know, close to 300 Kelvin, as we already discussed and assumed on previous slides. So here the atmosphere is fully transparent, and that's the so-called atmospheric window. Whereas in the absorption features, we can't see the Earth's surface, so we cannot see the emission of the Earth's surface. What we do see is the emitted radiation at a higher altitude, where the atmosphere above that altitude is transparent enough that we can receive that signal. And that is meant here with these different lines which shows Planck radiation curves at different temperature. So what we do see here in the center of the CO2 absorption line at 1.5 at 15 micrometer, that is radiation which originates at an altitude where we have about 225 Kelvin temperature. So that's pretty interesting. And let's now try to find a way how we can calculate such an observation. And therefore we use actually techniques which we already have derived. It's much less complicated than all these methods that we have discussed for the case with atmospheric scattering. So the first thing is that we divide our atmosphere in n layers. Each layer is homogeneous. That means that we have a constant temperature in each layer, and also the cross sections can be assumed to be constant in each layer. Just for a few words about notations, we have the altitude, obviously that goes from bottom to top, and the optical depth, which goes from top to bottom. The first thing is that what we do is we assume a plane parallel atmosphere as indicated in this figure, and for the plane parallel atmosphere we only have the z coordinate as a relevant coordinate, and the directional derivative dds is simply the cosine of the zenith angle times the derivative with respect to altitude. So our radiative transfer equation can be written as mu times di, and now the derivative with respect to optical depth, we have the radiance times the source function, the Planck source function. And in that equation, the cosine can be positive or negative. Positive values indicate upward streams, negative downward streams. And when we want to solve it, we want to integrate that, and then we have to assume certain boundary conditions. And the first thing that we can do is we say the height of our model atmosphere is at such a high altitude that we can assume there's no thermal radiation coming from space. So we say that at the top of the atmosphere, for a downward direction, the radiance is 0. For upward directions, we have to specify the radiance at the surface, and we will discuss that on one of the next slides. So with that information, we can integrate the radiative transfer equation, just as we did in one of the early lectures. And what we do see is that for the upward direction, indicated by the plus, the radiance as a function of optical depth and cosine is the one at the bottom times the transmission function. And then we have 1 over mu times, and now the integral of the Planck function with the corresponding transmission function. And we have to calculate that integral from the altitude where we want to calculate the radiance to the total optical depth. Situation is a bit more simple when we look at downward in downward directions. That is because of the boundary conditions there. The downward directed radiance is here given by I minus, and here mu's are always positive now because of this convention here. And then we have only left the integral 1 over mu integral over tau from 0 to the optical depth where we want to know the radiance field, the Planck radiation, and the corresponding transmission functions. So that's it. Doesn't look too complicated. Things become a little bit more complicated when we want to implement the proper boundary conditions at the bottom of our model atmosphere. So we assume that we now have a surface of a temperature Ts, and that can be described by an isotropic emissivity epsilon. The surface thus emits isotropic radiation, which is the emissivity times the Planck function or at the temperature Ts, but the surface also absorbs radiation with the absorptivity alpha is equal to the emissivity. That is the Kirchhoff's law. And in addition, the surface reflects radiation, and that is pretty much important because that is another source of light at the lower boundary. And the albedo, which describes that reflection, is equal to 1 minus the emissivity. Let us now assume that this is a Lambertian reflector. That means that the reflected light is isotropic as well. And then we can calculate the reflected radiances as the albedo divided by pi times the incoming flux, so the downward flux at the surface. And with that information, we can say now that the radiance at the bottom of our atmosphere at the surface in upward direction is the emissivity times the Planck radiation of the surface itself, and then the second term, which describes the reflectivity, 2 times the albedo, the integral from 0 to 1 over the cosine of the sinus times the cosine, because we want to calculate now this flux here, times the downward directed radiances. And you may ask what has happened with the pi. The flux is an integral over the azimuth and the zenith, and the integral over the azimuth we can already calculate. That gives a 2 pi. So that's why this pi actually went away, and instead of that we have this factor 2 here. So with this information about the radiance at the lower boundary, we can write the upward directed radiance as follow. We have here the term which describes the emission of the Earth's surface times the transmission function, and if we are in a very strong telluric absorption band, this function is so small that we don't see the emission of the Earth's surface. Then we have the term because of reflection at the Earth's surface, 2 times 1 minus the emissivity. We have replaced the albedo by 1 minus the emissivity, times the integral, which explains the flux, times the transmission function of that. And last but not least, the contribution of the atmosphere. So the integral over the Planck radiation at different levels, which is now here a function of optical depth. You could also express it as function of altitude, but this is much more easy to calculate. For the downward directed radiance, nothing has changed, so that is the expression we already discussed before, and here we only have contributions from the atmosphere. So these are the integrals that we have to calculate. You can discretize your atmosphere in homogeneous layers, and by that this integral over optical depth is straightforward to calculate. And to get a bit more familiar with the formalism, we now consider a very simple example. One homogeneous layer on top of the Earth's surface. For the atmosphere we assume a temperature T. for the Earth's surface temperature Ts. The surface has an emissivity of 1, and what we have to do is we have to calculate the integral along that line of sight with a cosine of the zenith angle mu. And we want to calculate everything at the top of that layer. That means that the expression for the upward directed radiance we must use, and the first thing is we can use tau equal to 0. That makes already things more easy. Then we can use the emissivity to be 1, which means that the second term becomes 0, and then we have to calculate the integral in the third term. So what we have is that at top of atmosphere we have the Planck radiation of the surface times the transmission function plus the Planck radiation of that layer. It's an homogeneous layer, that's why we can write it in front of the integral divided by mu, and then the integral over tau of the transmission function, and that is straightforward to calculate. And if you do so, you get for that integral mu times 1 minus e to the power of minus tau total divided by mu. And then what we can do is we can rewrite that and in the form that we have here, the difference of the Planck radiation at temperature of the surface and of the atmosphere times the transmission function plus the Planck radiation of the atmosphere. So that's a pretty simple expression. And now we want to interpret that. So let us assume that the optical depth, tau or tau tut, is cross-section times sigma, density times the geometrical thickness, and that we have only one telluric absorption. And now we assume that we know both the temperature of the atmosphere and the surface. And obviously, then these measurements can tell us something about the density of our trace gas. We measure a certain absorption feature, and that absorption feature can be related to the amount of the absorber in the atmosphere. So that's one case. Let us assume that we are in a region where there is no telluric absorption, so the absorption cross sections are 0. If the absorption cross sections are 0, then this term, the transmission function, becomes 1, and what remains is that we measure the Planck radiation of the surface, but from that we can determine the surface temperature. Assume that we know, and that's in the third case, assume that we know the surface temperature and the density. For example, we know relatively well how much CO2 is in the atmosphere. So we look at the telluric absorption of CO2, the 15 micrometer band we have just seen, and we know the surface temperature. Then we can use that absorption band to derive the temperature in the atmosphere. And last but not least, we consider the case that there is no difference in temperature between the atmosphere and the surface. And that is the fact when these two Planck functions are equal. So then we have here 0, and the only thing what we measure is, again, the Planck radiation of the surface or the atmosphere, because they have the same temperature. And in this particular case, there's no sensitivity at all to atmospheric information. So the fact that we need this is an example that we really need a thermal contrast between atmosphere and surface. Otherwise, these measurements do not tell us that much. I want to say a few words about heating rates, because the thermal infrared spectral range is extremely important for climate prediction, as the Earth loses energy in that spectral range and emits radiation to the open space. So let us calculate the heating rate, and we can do so from the solution of the radiance that we have just derived, and calculate first the fluxes which correspond to those. So we calculate the upward flux F plus at the frequency nu, and that is just the integral of the radiances over the cosine of the upward directed radiances. So that's why we have here the integrals from 0 to 1 d mu mu, which we have to calculate, and this occurs in all these three contributions. It's just a result of from the previous equation. And the same is true for the downward directed fluxes F minus, and here 2 pi because we have here the performed already the integral over the azimuth, that gives us 2 pi, and then the integral over the cosine of the zenith going from 0 to 1, and then that is the expression of the radians from the previous slide. All that can be solved. You see that we have here again an integral over angles that may remind you to the solution of the multiple scattering problem. And again here you can use a Gaussian quadrature to approximate that. Having these fluxes at each level in the atmosphere, you can calculate the heating rate. The heating rate was defined by the integral over all frequency of the divergence of the Poynting vector. You remember that. We can approximate that for a plane parallel atmosphere by the integral over the entire frequency space of the derivative with respect to the vertical coordinate of the difference of their upward and downward flux. So from these two equations we can calculate the heating rate, and having that, the so-called warming or cooling rate is defined as the change in temperature as response to the heating of the atmosphere, and we already derived that equation some lectures ago. This warming or cooling rate is the change in temperature with time. It's the heating rate divided by the heat capacity times the density of air. You can express that using the upper equation as a derivative with respect to pressure. Then you have here the gravitational constant divided by the heat capacity, the derivative with respect to pressure. And what we did here is actually that we have used the barometric equations, and again here the difference in the fluxes. In the thermal infrared, this warming or cooling rate is in general negative, which means that we have here a cooling effect, we lose energy. And let us have a look how this cooling rate looks like for certain absorption bands. So in this view graph we see calculations of the infrared cooling rate, the thermal infrared cooling rate of water vapor absorption on the left, CO2 absorption in the 1.5 in the 15 micrometer band, and ozone. The ozone absorption you remember at 9.6 micrometer band in the spectrum. We see different lines, and those are different atmospheric circumstances. We have here, for example, mid-latitude summer with a certain temperature profile and humidity, subarctic winter, that's a tropical profile, and that's the standard atmosphere, a certain reference atmosphere. So what we see is that the shape definitely changes going from water vapor to CO2 to ozone, but actually always we have negative values, which means a cooling. In the thermal infrared, the atmosphere is cooled, we lose energy. In the visible and shortwave infrared, we gain energy. What we also see is that the shape really differs from species to species. In water vapor, the main cooling is in the troposphere, because there most water is present, right? Whereas for CO2 and ozone, major cooling happens actually in the stratosphere. So let us summarize that the cooling rate really varies between species and the atmospheric circumstances, and that's why in a climate model you have to calculate that online to account for all these effects. This brings us to the summary of this lecture. So what we did is we discussed the Planck curve, which is, as any other radiation function or spectrum as well, a distribution function. And so it can change in shape when we go from frequency to wavelength. And we always have to consider that it's a distribution function, so we have to take into account the Jacobian of the transformation function. That's important. We also have found that spectra can be specified not only in watts per whatever, but also in temperature, under the assumption that the Rayleigh-Jeans approximation holds. That means that we are at a long wavelength with respect to the maximum of our Planck curve. And particular astronomers, when they observe hot stars, they are in that domain, that region, and that's why they talk about temperature to specify a certain radiance level. Then we discussed the concept of emissivity, absorptivity, and albedo, which all depend on each other. They are not independent when we have thermal equilibrium. That was the Kirchhoff's law, and with that knowledge we then finally found a solution of the radiative transfer equation, which is nothing else than the line of sight integration, or the formal solution of the radiative transfer equation that we discussed relatively early in that course. But be careful, it is a simple line of sight integration, but when we have an emissivity which is not 1, then the surface reflects light, which means that at the surface you have to know the downward directed radiances to calculate then in the next step the upward directed radiances. Heating rates, cooling rates, we discussed. The formalism was already known from the shortwave infrared. Can we calculate it straightforward using the fluxes which we derive from the radiances? And we have seen that we are interested in the heating rates or cooling rates in certain bands, spectral bands, with a lot of absorption features. And there are methods like the correlated K that we have discussed last week are quite important. So we are at the end of that lecture. Thanks a lot, and bye-bye.